Morning, everybody. Morning, Donnie. Morning, Hike. Nikolai, you are far from not first. Hello, Ava. Hi, Charlie. Ryan. Kimberly. Azra. I assume we'll say good morning to Rainey in about 5-10 minutes when he wakes up. So, on the agenda today, we're in period B. We need to finish Gravitational Force in Space. There is only, I believe, one question and a table to do in the second half of the document, so a little less than normal. Explain was a little longer than normal, but you didn't have anything to do in the explore section. Alright, so we explored the simulator yesterday, this simulator yesterday, on the motion of stars, planets, and the moon. Morning, Eric. That was in the explore section. We're going to review gravitational force in space, GFiS, and the PhET sim. We're going to review answers to the explain section, so hopefully you already have answers down. And then you're going to complete and evaluate and extend sections. Alright, when you're done, you're going to turn it in before midnight. Alright, before we really get into it, fun fact number 2. It takes a photon up to, let's zoom in on that, 40,000 years to travel from the core of the sun to the surface, but then only 8 minutes to travel the rest of the way to Earth. So the sunlight right now, outside, it's 40,000 years plus 8 minutes old. So when fusion happens, it takes 40,000 years to finally make it to the surface, because photons can be absorbed and re-emitted. So you have hydrogen fused together into helium, and then that photon goes out as energy, and that photon then reflects and then absorbs and re-emits all throughout the different elements and compounds throughout the sun, convecting, and then finally moving to the surface. Then it's just a straight shot to the Earth. That's the easy part. Yes, down in it shows you how big the sun actually is, because that takes 40,000 years for that little photon to make it all the way out. Alright, pretty crazy. So I pulled that one up because last week we were talking about fusion. I actually call that the random walk. Shows like the random path a photon takes out of the sun. But like I was saying, we're here today. It's all about the simulator. Review. Complete. See? I told you. Ryan, you laughed, so I know you're paying attention to what I said. Alright. So, the simulator. And I got a cool simulator from Hayden Walker, sent it to me yesterday, that really shows you the bending of space and why these objects always move in a curve. So Einstein's theory of general relativity, it's a good way to visualize it, because I don't actually have what I would use to help show it to you. You know, a sheet with different objects on the sheet. Bending of space. There's a simulator that does a better job that Hayden had. Alright, I'll show that to you in a second, or in a little bit. So this simulator, there's different presets. Obviously you could play around with it. Binary star and planet, 4-star ballet, slingshotting, binary star planet. You could do a sun, planet, and comet. See that really elliptical orbit? Alright, but we were just starting with sun and planet. Starting it, planet goes in a circular path around the sun, but the sun's also moving too. That's key to remember. The sun is also moving too. And at one point we were wondering, well, if the sun or the planet's mass gets bigger, what happens to the sun itself? And it's going to go in a larger orbit because the planet's pulling on it more. And they're always opposite each other, right? They're opposite each other in space. Always on opposite sides. And that's because the sun is pulling the planet to itself on the opposite side, and the planet's pulling the sun to itself on the opposite side. And they'll always try to pull each other to the opposite side, but because they have velocity, they'll never get there. Alright, so I kind of want to illustrate that point one more time so you guys get a better idea of what I talked talked about yesterday. Okay, if I have the Earth, right? Actually, let's make this a little bigger. If I have the Earth, and then I have a satellite. This satellite is experiencing the attractive force of gravity by the Earth, right? Earth is pulling all its matter and everything around it in towards the center due to gravity. But that just matches up with gravity, right? So gravitational attraction. Technically speaking, Sir Isaac Newton, he developed the gravitational attraction constant and the equation that we use to measure and calculate gravitational attraction between objects. He says that, yes, the Earth is pulling on the satellite, but the satellite's also pulling on the Earth. So just like the simulator, where you have the sun moving in its path, so too is the Earth. However, because the mass of the satellite is so much smaller than the Earth, then it won't actually really make it noticeable. Alright, so that has gravity. But the satellite was launched on a sideways angle, and technically it has velocity. So it's got momentum. Okay? When you have two forces at a right angle, so last year in 7th grade, you talked about balancing forces. If you have a force up and a force down, you have a force to the left, a force to the right. If they are of equal strength, then that object will not move. Right? However, if you have two forces at a right angle, you're going to make a 45-degree angle of motion, because the forces are technically unbalanced because of their placement. So the satellite moves this way. We call that a trajectory. Or, if you want to get real technical, it becomes the orbit. Because now the satellite's here, right? The satellite is experiencing gravity again, but it also has velocity. Oops, wrong color. But then it moves at a right angle between the two forces. And so what you get is, well, you look at that. A circular path. And that's how objects revolve, and that's what we call an orbit. Because of velocity versus gravity, however, the two forces are at a right angle, they are not offset. So they are not going to cause a collision. If velocity was going the same way as gravity, well, then the satellite would crash into the Earth. So if you slow an object down, it will crash into the Earth because it wants to fall towards the Earth. Okay? Except as it falls towards the Earth, it keeps missing the Earth. Alright? It keeps missing the Earth. So just keep that in mind. And we're looking at the warping of space. More mass, more warping of space. So a larger object, the more space will warp. If I make a smaller object, the less it warps. Okay? But then this object and this object are now going to roll basically into the pit of the larger object. So that's why objects move in curves. They follow curved space-time. They follow the curvature of space. So space is curved. It is warped based on mass. Until you get a nice stable orbit. See, I got a little orbit right there. Pretty cool. I'll probably link that in at the end of today as a comment on the daily post. Alright? So that was like a review. I'm going to review the answers to the explain section, and we're going to jump down to the evaluate and the extend sections. Okay? I know, Jake, you're confused on the extend. Someone sent me a remind just now. I saw they're confused on the evaluate. So we'll get there in a second. Let me quickly go through the answers to the explain section so we're all on the same page. All right? And I kind of went over a lot yesterday anyway. I wanted you to be on the right track. Make some initial observations below when you run sun and planet. Well, obviously, ooh, fix the mass. Go back. There we go. Obviously, I see the planet is moving around the sun. Okay. I see that the sun is also not stationary, however. It also has a small orbit of itself. Okay. So I was just showing you just basics, asking you to give me some basic information. Why do you think the sun is moving slightly? It's moving slightly because the planet is pulling on it, because anything with mass has gravity. Key information right there. Anything with mass has gravity. So yes, the planet is pulling on the star. Okay? So that's key to understand and key to put down. Anything, that's not the answer, but that should be incorporated in your answer. Anything with mass has gravity. Yes, you do have gravity. You have a gravitational field. You are warping space around you right now. However, you are so low in mass, and gravity is such a weak force compared to the other three fundamental forces in our universe that it's basically negligible. It's like the mass of an electron. Negligible. It exists, it's just tiny, and we basically round it to 0. All right? Next, investigate the different variables you can change. Answer the questions below. What variables are we able to change? Well, I can change mass, obviously. I can change an object's position, and I can change the velocity, right? I can change the position. You can see in position how the numbers keep wildly changing fast between positive and negative, right? Same thing for the purple object, the planet. Velocity, I can now change the velocity of the star too. All right, and then mass, I can make this 10,000. That's 1,000. 10,000, 100,000. I can make it 1,000,000. All right, so obviously I can change mass. Anything in this table is changeable, or I can click and drag it. All right, instead of just changing the numbers here. I could even technically, and we're going to talk about this in the evaluate section, I can change the number of objects. So that's actually another variable too, but we'll talk about that later. All right, we'll keep it sun planet for right now. So mass, position, velocity can be changed in the table near the bottom. Is there a pattern that determines which objects orbit another? What is it? Well, because there's a positive relationship with mass and gravity, objects will orbit other objects of greater mass. So an object will only orbit another object if it has greater mass. So essentially, it has a greater, if you want to think about it, in Einstein's point of view, it has a greater warp in space. And then it falls into its little well. Okay? Ooh. Got a binary system going now, so they're both in the curvature. Alright. I'm all over the place right now. There we go. Number 5, when the mass of the sun is changed, why does the planet's orbit change? So when you increase the mass of the sun, the planet's orbit becomes closer to the star. And if you decrease the mass of the sun, the planet's orbit becomes further from the star. Okay? Because there's less and more gravity involved. More gravity, it's going to pull that planet in closer. If there's less gravity, it's going to allow that planet to kind of move away from it. Alright? So the planet's orbit depends on the mass of the sun. Well, Mr. G, why do we have different planets at different locations away from the sun? Why aren't they all in the same spot? Well, that's because the accretion disk, the gas, dust, rock material that was surrounding the star when it was a T-Tauri star, a little baby, that accretion disk was starting to clump at different spots based on density. So we have different numbers of planets. All right? That's just a little aside. 6, when the mass of the planet is changed, what happens and why? When I change the mass of the planet, I went to like, what, 100? It brought the star closer to it. So it's very similar to, I think this was what, 10? It's similar to if you increase the mass of the star, you bring the planet in closer, but the orbit is a little different, right? So same effect on the planet, just different motion for the star. All right? So the planet moves in closer, whether the star's mass gets increased or whether the planet's mass increases. It moves in closer because there's more gravity, there's more traction. However, if it's the planet that gets larger, it increases the effect on the star, right? And that makes the star get pulled in different directions more as the planet orbits. And so the only way you really change the star is if you increase the mass of the planet. All right? Is it okay if I decrease its mass for an answer and then increase its mass for another answer? Why don't you tell me what happens when you do both? Just add on another half. If the planet's mass increases, what happens? If the planet's mass decreases, what happens? So when I say changed, I mean both. So if you guys don't have that, I'd maybe add that in there. Both increase or decrease. Yeah, because you guys can't really see comments. Changed is equal to alright. 7, when the mass of the sun and the planet are equal, what happens? This one's easy because there's just one change. What happens when they're equal? Both make them 200. They create a binary orbit, and they both orbit the center point between the two objects as they orbit kind of like each other. They orbit the center point. All right? Equal-sized orbits. So that was 1 through 7. And then we had 8 and 9 tacked on. Sun, planet, and moon. What do you notice about the moon's orbit? Why is it this shape? So the shape I wanted you to get at was the blue is around the purple. So the moon orbits the Earth. It doesn't orbit the sun. All right? And so why does the blue do this pattern? Why does it orbit the Earth and not the sun? Because I want you to discover that gravity is also impacted by distance. Okay? Gravity weakens exponentially as you increase in distance. So it's a severe drop-off. We say that's an inverse square law, in that it drops off squared as it moves on. Okay? So the moon is going to orbit the Earth because it's closer to the Earth. Just like when we talked about tides, right? That high tide is controlled by the moon, not the sun. Even though the sun has a greater gravity, a greater mass than the moon is much closer to the Earth than the sun. So it's going to be the moon that controls when high tide is, not the sun. However, we also talked about when they're in alignment, then yeah, you get a spring tide. Okay? So then, that was why is this do this pattern, or as Ms. Kiloff says, the pretty pattern. It's because it's orbiting the Earth, and that's because the Earth is closer to it. All right? Even though the sun has a greater gravitational pull, it's closer to the Earth because gravity is weak over distance. Okay? Then I asked you, we'll come back to what Nikolai wants to do. Change the moon's body to 3, mass to 2, what happens to the Earth's orbit. And because of my screen sharing or changing accurate and fast tab, you would see different things, but it would be the same kind of result. Different results, same action is kind of what I wanted to say. So moon had to go to 2, right? Start it. The Earth's orbit's a little off. You can see because it's kind of like tracing wider and shorter lines. The moon is getting a little irregular. to the point where, in my view, it's slinged itself out. So the orbit's getting, oh, they collided. I think this is what Hike saw yesterday, all right? So I'm not screen sharing today. I got this on my PC now. So now it's a little more accurate. Yesterday the moon was shot out of the solar system. When I move it on accurate, it got slung into the inner solar system and it became a planet. In this case, the moon just collided with the Earth. No matter what the result was, it's the same action. When you increase the mass of the moon, right here, it will make the moon's orbit more irregular due to the moon pulling on the Earth more by its increased mass and gravity. So when it becomes more irregular, that's where you're going to get weird things happening. Moon gets shot in towards the sun, becomes a planet, gets shot out of the solar system, or collides with the Earth itself, destroys the Earth. Okay? So it becomes more irregular. The Earth's orbit in of itself is going to also become irregular, but also becomes like shorter. It's moving closer towards the sun because the moon's kind of pulling it. All right? So they both become irregular, really. And the moon eventually leaves the Earth. They become irregular and the moon leaves the Earth. Nikolai wants me to set body 3 to 2 and then make it really fast. So instead of accurate, you just want to see it fly. I still got a collision. It's kind of interesting, though, that how lag can play a factor in the calculation. Because this is just like a big calculator. It's calculating Einstein's equations, and it's using Kepler's planetary motion laws, and I don't think it's using any of Einstein's relativity, but this simulator is doing math calculations every time you hit start and then you let it run. So the faster you make it go, the more rounding it has to do and the more errors it makes. Okay? So if you slowed it down, it gives more time for the computer to make calculations. Alright? So it gets more accurate. If I'm screen sharing my Chromebook to my PC, it causes really interesting changes in that it also probably slows it down. So you can probably make it really super slow if you screen share a Chromebook. It's just interesting. Yeah. But what did you see, Nikolai? The extend question. Scientists are beginning to develop the technology to observe other stars distant from our solar system. It became a planet. Yeah, that's what I had yesterday. So, yesterday I screen shared and ran it on accurate, and that's what happened. So I really slowed it down. It might actually depend on your internet connection too, if you think about it. Scientists are beginning to develop the technology to observe other stars as from our solar system. So we have the Hubble Space Telescope. We also have the James Webb Telescope that's going to be launched next year. Okay, they can detect planets orbiting some of these stars. All right. 10, without seeing exoplanets. We can't really see exoplanets. So the exoplanets that you did research on, or you heard about, or we talked about, we can't actually see them. A lot of those are artists' pictures based on data, spectral analysis, based on gravitational movement. How do scientists know the planets are there? How do scientists know the planet is there? So, if I could do this, How can I do this? Oh, we got a tape measure. That's cool. So if I run sun and planet, I let it go. How could you tell that there is a purple ball going around the sun without seeing the purple ball? What could I infer allows the planet to exist? And this is not rhetorical. If you think you know, you go ahead and you tell me. How would I know that the planet's there? What else can I see that leads me to that clue? Nikolai ran some strange simulation. You got it to go back to a moon. That's interesting. Alright, well, what if I do this? What if I increase the mass again? How would I know that there's a planet there if I couldn't see the purple planet? What is the sun doing? Is the sun perfectly stationary? There you go, Hike. Okay? The star's moving in its own orbit, its own circular path. Okay? We call that a wobble. If there was no planet, it would be stationary. Good. Alright? So, how could I, like, show you that if there was no planet? Let's see if I can, like, just, like, put it over to the side. Like, kind of, like, get rid of it. Gravity took over. I can't hide it, can I? If I just set it out. Nah, gravitational effect's still there. So you would see no wobble. You would see no orbit, just like you said, Hike. Okay, the planet would be stationary. Alright, so we can actually use like almost like a little tape measure, and we can measure the wobble. If the wobble is small, then the planet is small. If the wobble is big, then the planet is big. So that's how we know whether the planet is the size of the Earth, the size of Jupiter, the size of Neptune. We can use the wobble of the star. So we go back here without actually seeing exoplanets. How do scientists know the planets are there? You can look at a star in its orbit. You can see it wobbling. You can see it go in a circular path. The bigger the movement of the star, the bigger or the larger the planet. Because the larger the planet, the more gravity it has, right? So we can look at the motion of the star. But also there's another way that we haven't really talked about, or we have talked about. Obviously, these are not answers. You need to actually plug these into your own words a little bit more. Okay, I'm just giving you quick notes on what to kind of aim for. All right, and then Rainey kind of follows up. There's a second way to observe a planet indirectly, and that's using its shadow. So you can run what we call a transit. Okay, so if I Google one of the inner solar system planets, like Venus transit. So something like an eclipse, except it's not taking up the entire sun. This right here is the shadow of Venus across the sun. Okay, you can see other pictures. Sometimes there's a plane there. All right, it gets caught in the way. In a transit, we are looking for the shadows. And our telescopes can actually measure the loss of brightness from a star from a tiny planet moving in front of it. So we use the transit method. We look at the dimming of a star to determine size and then to determine what the planet is made out of, because the light goes through the atmosphere and refracts and makes its own spectra. And we can find out if there's oxygen in the atmosphere, or if there's water in the atmosphere, or if there's sulfuric acid in the atmosphere like with Venus, or if there's methane in the atmosphere for a possible biosignature of life. Okay, we can analyze the atmosphere as light from the star passes through the planet's atmosphere and then to us in Earth. All right, so that is the first way we found exoplanets. And the next way, there is also the transit method. And again, if you're interested for more information, go watch Does the Sun Have a Shadow?, which was asked as a joke by John Leach, I think, but actually had a really cool answer that was part of the GSA if you did App B. Okay? So that's the extend. Just one question, two parts. The evaluate box. So there's 4 real variables. I added in number of objects from our answer up in number 3. So I added this one from additionally from number 3 because it's in the chart. Oops. So I want you to be able to complete this table based on what you've seen, what you observed. This is the final evaluation of this simulator. All right? Massive objects. There's 2 things you can do. Increase or decrease. When you increase the mass, what's the effect? When you decrease the mass, what's the effect? Based on gravity, what happens? So you're looking for cause and effect of each variable. So I can either increase mass or I can decrease mass. Guess what, guys? A lot of these are going to be increase or decrease. All right, so increase or decrease, what will gravity do in response to both? Okay? So go back up, think about the relationship. They have a positive relationship, all right? Which means, yes, you can decrease something. What happens in a positive relationship when you decrease the independent variable? The dependent variable will also what? All right? So think about relationships and correlations that we've done all year, really. Okay? I'm going to skip over positioning. I'm going to go to number of objects. Again, I can either increase or decrease the number of objects. I can increase or decrease the velocity of objects, right? So when I increase or decrease the number of objects, what's going to happen? So I can even just run it, right? So this is 1. I'll get rid of the tape measure. Yeah, let's just do this. That's this one, right? We're familiar with this one. Okay. Oh, I go to 3 bodies. Okay, we're familiar. Okay, so we had another planet, right? Well, what if we all put them kind of in the same spot? So let's give them all a very similar position and then the same velocity. So Try to make this equal. Position X is 142, so we'll do 142. And then 0. Oh, I don't want to give them the same position, so how about 70 and 0? No, now I'm over that one. 100 and 0? There we go. Alright, just go 70. Keep it at 0 for the Y. So that's a difference of 30, so let's go 130. So now they're all equidistant from each other. 130, 100, and 70. So it's like an x-axis, right? 70, 100, 130 to infinity. Velocity, I want to match green and purple together. So 0 and 140. So we'll make this 140. That's 0, 0. I want the same mass. So we'll just do 10. So everything's the same. They're same mass, same velocity, same direction of the velocity, but I just added more objects. That's it. That's the only variable I changed. So the star had a crazy elliptical, or a crazy little like zigzaggy orbit. Green planet had almost 2 orbits, and all planets were destroyed except for purple. Purple reigned supreme. So, go back here. If I increase the number of objects and I decrease the number of objects, and then the same location, roughly, what happens to the order? Am I going to increase chaos? Am I going to increase the destruction? Am I going to make it more irregular? What's going to happen to the orbits you can almost think about? All right, so you can't really change gravity here, but you can. Orbits will do what? So maybe describe the orbits. Okay. Velocity of objects. If I increase the speed, what happens to the orbit? Because the faster it moves, go back here again, the faster it moves, the more velocity it has, you're going to widen out that orbit. So the faster it moves, the wider the orbit gets. To the point where there is something called escape velocity. The speed an object needs to break free of gravitational attraction from another object, or to break free from the curvature of space, to get out of the curve, to go up the curve. You need a lot of energy to do that. So for velocity, what will the orbit do if you increase velocity? What would it do if you decrease velocity, right? There's our typical starting point. Oh, what if I crank up velocity even more? What happens? Right? What if I slow it down? What happens? All right? And that's just kind of what you're doing in this evaluate table. You're looking at cause and effect, increasing the number, decreasing the number, increasing the velocity, decreasing the velocity. What happens to the orbits? What happens to gravity? Okay? Positioning is a little different. You can move an object closer, or you can move an object further. So when you move an object closer or further, what happens to gravity? Let's reset it. If you move an object closer, or you move an object further, what happens to gravity? What happens to the orbit? You can also kind of think about too. So, I mean, both of those are acceptable, but I want you to focus on gravity because mass and distance or position are the main variables in gravity. Okay? And then the number of objects and velocity, they'll impact the orbit. They can't really impact gravitational attraction. But these first two are really important, and they are what directly affects gravity. All right? Downey asks, so do we have to do both increase and decrease? Yes. Describe to me, increase the mass of the planet, decrease the mass of the planet, move the planet closer to the star, move the planet further from the star, and tell me the effect. Okay? You're just filling in this chart based on what you see in the simulator. Any other questions? How do you decrease the number of objects, Ms. Kildoff? You can only have 2. So you can't go any less than 2. What I meant by that is, so by decreasing, obviously, whoops, where am I? Decreasing number of objects means 2. So 2 objects, right? And then increasing would be anything greater than 2. How do you get objects greater than 2? Right here, bottom left of the table, that's at the bottom of the simulator. I can click 3, I can click 4. I can't go less than 2, but I can go up to 4. So starting at 2, that would be decreasing, and then 3, 4. Any other questions? So if you have questions throughout the day, again, send them by email, send them by Remind. This document is due before midnight. Not as long as others. There were no explore questions. There was 9 explain questions. There was 1 extend question. And then there was a table at the end in the evaluate section. So you had 10 questions plus a table. 1 point for each of those questions, 10 points, and then 4 points for each of those variables in the table makes this out of 14 points. So when you get it returned to you, it'll be out of 14. Okay? There is no DNAC this week. There are no DNAs. So you don't have to worry about filling in a sheet. There is no quiz on Thursday. You guys do not have class tomorrow. But obviously, if you're missing something or you didn't finish this, you got to get it turned in. All right? Deadline those before midnight. And then following Tuesday, because we have Memorial Day on Monday, we'll start getting into, or continuing, talking about the Earth itself, the layers of the Earth, and how the Earth works on the interior instead of the exterior with the atmosphere. Kind of wish I changed the order now, looking at it from the beginning of the year. Should have done Earth before when we did weather. I think that would have been a good transition to talking about the planets. But alright, if you guys got no questions, I will catch you on Thursday. But you can do revisions tomorrow if you're interested. If you're interested in revising DNA Excel, send me an email and I'll give you what you should be working on and answering back for a revision. Okay? I think there will be a meetup. I haven't talked to the other teachers yet. I will let you know on Thursday, Ryan. Alright. Catch you later, Hike. Bye, Ezra. Bye, Ryan. Bye, Rainey. Bye, Ava. Bye, Downey. See you, Charlie.